Okay, so last time we introduced the idea called Hoare triple. Okay, let me review very quickly about it. And today we'll go into the heart of it, which is to do some little bit proof. Okay, so given a program where you got precondition Q, you got postcondition R, and also S over here is implementation. Over here, the structure for S is recursive, which means it can be simple assignments, it can be if statements, it can be loops, for example. That's something we'll build up the complexity. But it's called correctness predicates, meaning that given a piece of program with precondition and postcondition implementation, you can somehow translate it into Hoare triple. Okay, again, the example, let me show you very quickly the example we did last time. Okay, if you remind yourself what we did last time. Let's say this is a program we have where we got precondition, we got postcondition, we got some simple implementation over here, right? So this is the corresponding Hoare triple that we can translate. Okay, you can see curly brackets over here for the precondition and curly brackets over here for the postcondition, right? What you put inside in the middle is the implementation. Okay, that's syntax-wise. Okay, first of all, make sure you're comfortable with the syntax. Okay, and then second thing, eventually, given any Hoare triple corresponding to your program, you can be proved either as true or false. Okay. And the proof rule will be the focus today to see how we can prove it. In order to prove the Hoare triple, you have to understand something called the weakest precondition. Okay, I will also get there today. Okay, to get some intuition first. Okay, and then there's some terminology here you want to know. One is about termination. Usually, if your program does not contain any loops, you don't have to worry about termination. If you only got assignments, if you only got if statements, or you only got sequential composition, right? You don't have to worry about termination. If you got loops, you have to worry about it. We'll get there too. And so we talk about something called partial correctness, which means assuming that your program is going to terminate, let's focus on correctness. Okay, and both together will be called total correctness. Okay, Hoare triple here. Okay, so now what I would like to do is give you intuition about how you can interpret that, okay? And then we'll talk about weakest precondition. And we also went through the different combinations over here, okay? So that's something you can review, okay? So what we'll do is this particular proof rule, okay? So given this particular Hoare triple, how do we prove it? Either prove it or disprove it. Either way, okay? Here's the formula, and I'll tell you the formula first, and then we gotta understand what it really means. So this is something you gotta prove. Overall, you have to prove an implication overall. The antecedents for the implication over here is Q, the precondition for your program. You are saying that my precondition Q should be stronger than the weakest precondition. For what? The weakest precondition for the program S to establish the postcondition R. That's what it says. Let me say that again, and then I'll give you intuition. Again, we're trying to say the Hoare triple over here, overall, is going to be either true or false that you want to prove. We're saying that you want to prove the following implication. Given the precondition you have for your program, is it stronger or no weaker than? Is it stronger than the weakest precondition for S, the implementation, to establish the postcondition R? That's kind of the logic. Okay? But now let's see a little bit diagram to help you visualize the situation here. And for WP, we haven't talked about it. There is a systematic way to calculate it. You have to know. Okay? And we'll do lots of examples today as well. Let's have a look at over here. Okay? Remember last time when we started the lecture, we say that in order to understand predicates being either weaker or stronger, you think about the set of satisfying values. If the set is bigger, that means the predicate is weaker, right? If the set is smaller, so that means the predicate is stronger, right? That's what we said last time. So now let's think about this particular relation, and then I can take some questions. And we can also do examples. Over here, we say Hoare triple over here. Okay, let's think it this way. This is the Hoare triple we're given. Let me highlight it. That's what we're given over here. Now, given this particular Hoare triple, we're going to focus on just this part first. Given the implementation S And given the post condition we would like to establish upon the termination of the implementation, right? R. These two things. What does that mean? So that means we have this particular implementation that we're going to execute. I just use an arrow to represent. The ending states or the terminating states, the resulting state, like a post states, is going to be all the satisfying values for R. Are we okay so far? Okay, I'm just saying after executing the whole program that's outlined in S, you're going to end up having one of the state that's in R, which will satisfy R. Okay? So now, having these two things over here, there is a way to calculate what could be the weakest or the largest set of states for you to start S, such that you can establish R. Okay? So now over here, let's have a look at this. So now if you look at this, let me change the color over here. So you look at that, this is the orange part is really something you want to calculate conceptually. Okay, I'll write it down over here. Okay. So now what we want to say is this. So this is the largest possible set where any starting states from here can guarantee the execution of S. The execution of S, well, the S over here will establish post-condition R. Okay, the orange part. We haven't talked about exactly how to calculate that just yet, but we will. Okay, but for the next one or two examples, I'll just tell you what the weakest precondition is, just to see the diagram. Okay. The green part is what you're given in your program, the implementation and the post-condition you want to satisfy. The orange part is something you can calculate. Okay, there's one more missing puzzle over here. What about this guy here? So now you're saying that over here, the green part over here, which is also given. So the Q over here is the precondition of your program. So now you're asking whether your original precondition there is every state in your existing precondition allowed by the weakest precondition. In this particular diagram, it is. So this diagram shows you the Hoare triple should be true. What would be a case where the Hoare triple is false? I'll draw that right away. Okay. Again, let me draw from scratch. Imagine that this is your program S. Okay. This is the set of states that's specified by your post condition R. And assuming that we have a way to calculate the weakest precondition over here to say, starting from any of the satisfying state in this particular orange part, right? WP for S to establish R. However, what if my precondition conceptually looks like this? Conceptually. Which means the Q is not exactly a subset of WP. So now, Hoare triple is going to be false. For example, over here, you can see over here, this state over here, right? Think about this particular state. This is allowed by precondition Q. Precondition Q, but not allowed by the WP for S to establish R, i.e. Q is not a subset of WP. Well, actually, you know what? Let me not talk about subset because they are predicates. I.e., Q implies WP of, for S to establish R, is not the case. Yeah, I just want to talk about concept a little bit, okay? So always have this, these kind of concept in your mind, okay, when we want to do the calculation. Guys, any questions so far? We okay? Yes, go ahead.
Just like you think that it's like whatever you showed in previous note, then like this note is something different, right?
This is a little bit different, yes. First of all, always you start with the implementation S and also the post condition R. Okay, always start with that. Always start with S and also R. And then accordingly, you can calculate the orange one, first of all. And then you want to compare this orange over here against the existing precondition. If it is the case that Q is exactly a subset of the orange one, then you're fine. That means the original program is correct and the Hoare triple should be true. On the other hand, for example, over here, if there is at least one state in your precondition that's satisfying, but it's not allowed by the weakest precondition, then it's not correct. Yes?
Doesn't necessarily mean that Q is weaker.
Oh, yeah. Oh, okay, good. So there are different ways you can actually make Hoare triple false. Okay, let me show you again. Okay, it's a good question. There are at least two different ways. Okay, how can a Hoare triple be false? Conceptually. Okay, basically, let me start with this. Okay, so we have, again, this is our program, and this is our post condition, right? And this is our WP, okay? WP over here, and then for S to establish R. Let me give you two cases where it's going to be false, okay? Case number one, I'm going to do in red, like this. In this case, my precondition is weaker than the weakest precondition. It is not supposed to be weaker because it said it's weakest, right? You cannot be weaker than the weakest, okay? So now over here you can see this is a counter example. Okay? And another case is something we just said previously. Use another color, let's say purple. In that case, maybe you will simply just get something like this. Let's say this is your Q. In that case, this would be a counter example. Okay? Yes, I think that these are the two typical ones. Yes, question?
There's also a third case where there's no overlap between Q and...
Of course. Basically, we'll talk about it like a set theory, right? As long as it is not the case, your Q is a subset of WP, then it's false. I'm just trying to show you a different example, right? Of course, as you just mentioned, I can talk about another one. I'll use another color here. Let's say your Q is simply just over here, right? Does not overlap. That's also false. Okay, let's now make a little bit more concrete. But as long as you're comfortable with this conceptually, I think it's a good start. Okay, that's very important. Let's see what we got previously. Remember this program here? Okay, so now let's see this. This one here is telling us exactly what's happening here. Okay, again, we haven't talked about how exactly you can calculate WP. It's given just for now. Okay, we'll do that in a moment. Okay, so now for this guy here, again, you should know how to translate it. So now I will do is I larger than 3. That's the Q, and then that's the program. I is assigned to I plus 9, and then I larger than 13. Okay, let me fill in the blanks over here. I larger than 13 is the post condition I would like to establish over here. And this is the implementation, I plus 9. And the existing precondition I have is I larger than 3. Okay, I'm just filling them in. It turns out the WP over here, I'll write it down. The WP, you can take it for granted just for now. WP for I is assigned to I plus 9 to establish I larger than 13. Okay? And WP here is, by the way, it's called weakest precondition. Okay? Weakest precondition. And the weakest precondition, you think about it like a function. You will take two arguments. The first argument here is just a program. Okay? It's a program. And the second over here is just a predicates. Okay? Typically, you just put a post condition there. Okay? What's the result for the weakest precondition? Well, it's a precondition, like a predicates. One moment. So now, take it for granted, it will simply be I larger than 4. Okay. So far so good? Okay. If it's I larger than 4, I think this diagram is a little bit inaccurate. Okay. Let me just get rid of this. I should really shrink it down. Okay. You know what? Maybe let's do it the other way. Sorry. I should have fixed my notes a little bit. Okay. First of all, let me move this guy here. Okay. I should really make it bigger. Because turns out this program here is not correct. Like that. Okay, so now I larger than 3 is my precondition over here. It turns out it's actually weaker than the weakest precondition. Okay, so now if I put it in over here, you can see it's I larger than 4. So I larger than 4. Would you agree I larger than 3 is weaker than I larger than 4? Right? Something we said. Okay, so that's the correct diagram. Okay, I'm fixing it. Okay. Of course, you don't really want to use diagram like this to prove it every time. That's not the way to go. But to begin with, I want to show you. Okay. Okay, so now in this particular case, because you can see I larger than 3 over here is not a subset of I larger than 4. So I larger than 3 implies I larger than 4 is not the case. So this program cannot be proved correct. Okay, you just give some counterexample. Okay, let's see another one. Another one here is this. Okay, this time this is okay. What about this guy here? Okay, similar idea, very similar. Again, I larger than 5 is a different precondition, seems to be stronger, right? And then I is assigned to I plus 9, and then I larger than 13. Okay, again, the WP, as we said before, for I is assigned to I plus 9 to establish I larger than 13. Okay, it's going to be I larger than 4. Okay, the WP, we're going to talk about how to calculate in a moment. Take it for granted for now. Let's fill in the blanks over here. R over here is I larger than 13. S over here is I is assigned to I plus 9. Somehow, we can calculate the WP over here is simply just I larger than 4. Okay, once we have done this, if we check to see what the existing precondition is I larger than 5, which is stronger than that. So this will be okay. So that means every valid input value that's allowed by the WP is also allowed. Only those that will be allowed for our precondition. No more than that. Guys, any question about this? Conceptually, right? We haven't done any mechanical proof just yet, but we will. Okay, you can come back to me, no problem, but let's see a little bit more, okay? Okay, the next one will be, we'll talk about WP, okay? So now the WP is called the weakest precondition here, and what about the programming statement there, S, okay? You can put either assignments, that'll be the first one to do, okay? And we'll talk about alternations or conditional, if then else, basically. And also, sequential composition, it corresponds to the semicolon you put in Java or Java-like language. Being if was simply just empty line. And then you also got the loops, okay? So that means this programming structure over here is very general. It applies not just for IFO for this course. So once you learn about the technique, you can also feel free to apply to part of your program for Java, for C, or for Python. Okay, it's definitely applicable. Okay, now we're going to see how to calculate WP. Okay, any questions so far about linking, Q, R, programming statements, and also WP stuff? Okay. Let's have a look at some example, okay? Okay, so this part here, we already said it. Okay, so now, when we program IFO, we actually use the O keyword to denote, for example, we say old X or old balance to say that that's the value in the pre-states. So when we do the proof, we use some similar notation. We don't use old. So whenever you want to really denote the value of your variable in the pre-states, you would say 0, subscript, okay, x0, for example. And when you say x, it simply means the current states, okay? Something very quick to tell you. For example, if you have this over here, I'm saying that the post condition I would like to see is be equals B0 minus A, the old value of B minus A, right? Like OB, okay? And then there's the implementation, and in the precondition, basically every variable there is a pre-state value. So you don't really have to say B0. You don't have to, okay? Okay, let's see the very first one. This one actually is interesting, even though it's very simple, but let's get a right intuition about it. We have WP here, and the first parameter there, the first argument, is an assignment, a single assignment. X, assuming that X is in our scope, is a variable, is assigned to some expression E. Let's say it's type correct, okay? And then we want to say, what would be the weakest precondition for this particular assignment to establish certain post-condition R? R can be anything. R can be maybe X should be larger than 0 afterwards, or X should be in between 1 and 10, right? So now, this one here, we can just take it for granted, but I'll explain to you what the intuition is. Overall, WP is going to be a predicate. It would be just R. However, you have to substitute every free occurrence of X by E. That's the definition. But it sounds a bit fancy, right? But it's not. We'll do example, don't worry. It's very intuitive, okay? Let's do one example here. Let me show you a little bit of diagram. Let's say this. The post condition I would like to have after this assignment is X should be larger than 0. Let's say, okay? And then the only implementation I have in my program is to assign X to be E, okay? So now you tell me, what should be the weakest precondition? E is greater than 0. That's it. E is greater than 0. So what I'm doing over here really is, X larger than 0 is really the R I'm talking about over here. And then I'm going to substitute every occurrence of X that's free. In this case, only this X. Substituted by whatever thing I'm trying to substitute it in the implementation, right? Substituted by E. And what this will do is replace X by E. So that'll be E larger than 0. Conceptually, that's what we are doing here. This one is not exactly concrete, but I want to show you the diagram just to tell you what's going to be achieved, and that's how we want to achieve it, but what should be true beforehand. Okay? We okay with this? Okay, it's not as bad. Okay, let's do examples. Any questions so far? Okay? Yes? No, we don't have to get that far about duality. We don't have to. Michael, you okay? Let's see the first example, okay? Let's see this. What would be the weakest precondition for X? Well, let's say my program is I'm going to increment X by 1. And the post condition I would like to establish is X should be larger than its initial value. What would be the weakest precondition then? Well, I heard something that's correct, actually. True? Okay. Yes. Well, even if X is negative, let's say X was minus 4. Minus 4 plus 1 give you minus 3, right? It seems like any value of X is going to satisfy this because you increment something. That's not negative, right? But let's see how we can calculate this, okay? So now, how do we let's get the syntax right, okay? You're going to calculate the weakest precondition for X is assigned to X plus 1. And then what you want to establish is X larger than X0, which means old X, okay? Start with this. And then how do you calculate? What you would say is, this is the recommended style you can try, okay? That should be equal to, okay? And then you give some reasoning over here. So you can simply say WP rule for assignments. Assignments, okay? So that means we're going to have X larger than X0. First of all, I'm copying this post condition verbatim. right? And then I'm going to replace every free occurrence of x by, you can think about this part over here is the e that we talk about, right? X plus 1. Okay, and then let's go with a little bit substitution here. So that means we're going to replace x over here by x plus 1. That means x plus 1 larger than x0. Okay, so here be a little bit careful. So I think sometimes you may just want to have some old value to help you. Okay, think it this way. When I do this orange part here, when I say x is assigned to x plus 1, this x over here is really x0, right? The very initial value for x. I'm trying to increment x. Okay, so now it will be more helpful if I say x0 plus 1 larger than x0. So now if you reduce that, it will be 1 larger than 0, always true. So what does that tell us? That tells us the weakest precondition for this particular implementation to satisfy this postcondition is simply true, right? Any precondition that's stronger than this will be fine. Well, thinking another way, can there be anything that's weaker than true? No. So that means this program will always work. Doesn't matter what you put over here. Anything is weaker than true. Okay, so what this tells us is this program works. Program works for any precondition. Okay, yes, question.
Go back to the previous slide.
Yes. Yes.
So let's say we're setting up a postcondition, we're trying to do complete postconditions, and say something like ensure that the certain values remain unchanged. Like how would we show that in the, like using this kind of
Yeah, so I think, you know what, that's something I'll try to address a little bit in the last lecture, like next Tuesday. So the question was, remember, well, so far the most kind of complicated postcondition we have to write is like in the complete postcondition lecture to say across maybe current, all current D twin, and then do a serious implication stuff. That's definitely can be applicable to this approach, but that will require a little bit more sophisticated calculation. Maybe that's something I can mention a little bit in the last class. Okay, but for now, let's focus on some simple example just to get you comfortable first. Do we have any question for this very first example, which is calculating WP? Okay, and having that being true simply means any precondition will be fine, because anything will imply true. Okay, let's see the second one. Well, what will be the WP over here? X equals 22? If you think about it, it makes sense, right? In order for me, after incrementing x by 1, I want to get x equals 23. Of course, x got to be equal to 22. It makes sense, right? We'll start with something very simple. But how do you calculate that very quickly? Okay? And then I'll tell you another thing here. For example, let's say this. For now, let's say at the moment I got this particular precondition here. X larger than or equal to 22. Let's say this is a question on your exam. Here's a question. Is the following Hoare triple true? I heard no, but why is that? It must be no, the other way. This one is weaker than the weakest precondition, but it shouldn't be, right? In order to be correct, you got to be stronger. It cannot be weaker. Okay. Okay. Guys, let's go over the steps. Okay. So let's say I change the question a little bit to make it a little bit more relevant. Okay. So now, is this program correct? That's a question. And there will be 2 steps you have to write down in order to conclude. Step number 1. Calculates the WP for this implementation over here. X is assigned to x plus 1. For that to establish the postcondition over here. Calculate that first. That's step number 1. Step number 2. Prove that the existing precondition, x larger than or equal to 22, should be no weaker, right? Should imply no weaker Because if that's weaker, you have some value that will actually violate the postcondition. No weaker than WP for x is assigned to x plus 1, and then x equals 23. Okay, that's the steps. So the pattern here is always the case. The only thing that would change would be maybe the program might be a little bit more complicated, involving if statements or loops. And also the postcondition might be involving universal quantification across, or it might involve certain other things. Okay? But the pattern is always like this. Okay? Always get the pattern right. And let's do that quickly. Okay? Step number 1 is usually the more difficult part. You got to get right. Okay? Step number 1, how do I calculate? WP of this is equal to, according to the rule, okay, WP rule for assignments. Okay, so that means I got x is assigned x equal 23, and then I'm going to substitute every occurrence of x by x plus 1, the e, right? That's the e. Okay, which is that what that will do is substitute this x by x plus 1. Okay, so I got x plus 1 equals 23, which is equivalent to x equals 22. Okay, that's the answer from step number 1. That is the weakest precondition. And somehow this weakest precondition is very strong. It has only one member in the set, right? Which means if x is not 22, there's no way for you to establish that postcondition. Okay, so now, what about step number 2? Step number 2, you're just going to replace this guy over here by your conclusion from step number 1. Does x larger than or equal to 22 implies x equals 22? No, right? But how do you disprove to the greater? Counterexample. You got to give counterexample. Well, if you can prove it, prove it. If you cannot prove it, give a counterexample. Not the case. Any counterexample? 23, for example, right? Cannot be 22, right? For example, not the case. For example, x equals 23. In that case, it will simply make this true, but make this false. Okay, so true implies false would be false. That's really the pattern you have to follow, okay, for the exam to be. Of course, if you really believe there's another pattern that will work, feel free, and then we'll judge. But I would suggest to be safe. Okay. Any question about the pattern here? Step number 1, calculate WP. And so far, we only learned about how to calculate WP for assignments. Step number 2, whatever you calculate from step number 1, try to prove that your existing precondition implies that. If it doesn't, give counterexample. Okay. And it's almost guaranteed you'll get a question like this in the exam. Okay. But I just want to tell you first. Yes.
If we can just find the precondition just by looking at, do we have to go through the steps of doing all the substitution and all that, or can we just say the precondition is x equals 22?
I would say, number 1, you wouldn't get a simple case like this in the exam. If you're really given a case like this, be my guest, you can just say that WP is just x equal 22. That's not a problem. But most likely you'll be given something that's more complicated. Then you better show all the steps.
So you're at the end of step 1, x plus 1 is equal to 23, and then are we checking to see if that implies specifically x plus 1 is equal to 23? Like, I don't understand this step a lot.
Okay, so you're okay up to here, right? Are you okay up to here? Would you agree this is equivalent to x should be equal to 22? Well, you move the plus 1 to minus 1 here, right? Okay, so now this is the answer you get. So this is the WP for this, so this is the answer for this particular WP. Okay, and then we want to make sure the existing precondition over here entails or implies this WP. If it does, it is correct. If it doesn't, it's not correct. Okay.
So
Correct. You need to do a little bit of simplification. Where? Sorry, which one are you talking about? Are you talking about this one here? Okay. You're here? Oh, no. Here I'm saying that, let's say you're given this particular program. if somebody else passes to you this program, asks you, can you prove to me if this program is correct? That's something that's given, okay? In order for you to judge whether that's correct or not, you have to calculate WP based on these two components first. And then to see if this existing precondition implies the WP over here, okay? Chelsea? You mean just the pattern or the pattern? Every time you're given a program to prove if that's correct, you'll be given three things, okay? You'll be given its precondition, you will be given its postcondition, you will be given its implementation, right? Of course, depending on the example, that could be a little bit different, but the pattern will be always that, okay? How do you prove whether this is correct or not correct? Here's the two steps. Step number one, try to see, given this particular implementation, what would be the weakest precondition to start with in order for this particular implementation to, upon termination, establish the postcondition over here. Calculate that first. And so far, we only learned about how to calculate for assignment. We'll do more in a moment, okay? Once you have done step number one, step number two is to examine this particular existing precondition. If it turns out to be stronger than the weakest precondition, then it is correct. If it's weaker, then that's not correct. So that's why we are trying to prove this implication over here. Okay? Again, you can see one more note for you. You can see this is the given precondition. And this one here is a WP you just calculated. Right? As long as the implication holds, then that's correct. That should be true. Otherwise, give counterexample to show that's false. Okay. All right. Let's do a little bit more. Okay, that's about the assignments over here. So now let's say every time you're giving this particular program here, okay, let's say, so this is what you got to prove. You want to say the precondition Q implies the postcondition R with every free occurrence of X substituted by E, right? That's exactly the rule, okay? Nothing new, okay? And that's the example we just did, okay? That's fine. And that's the second example we also just did, okay? Not skipping anything. Now, what we want to do is do for if conditionals. Okay, let's have a little bit discussion over here. Okay. The if conditional, number one, pay attention to those two things I want to show you. Okay. I say if Boolean condition B is true, I'm going to execute S1. Otherwise, not B. B is false. I'm going to execute S2. And then, upon the termination of this particular if conditional, I want to establish the postcondition R. That's what it is saying. But now, what should be the WP? Okay, we'll have discussion, but I want to ask, know something to you. The S1 over here and S2 over here, they are arbitrary programming statements, which means S1 can be a single assignment. S1 can be another nested if. S1 can also be another loop, just arbitrary. Okay? And also S2 as well. Okay? So now we want to think about exactly how we can come up with the WP. I have choices for you. Okay? I got choices over here for you. Okay, we'll discuss it, and then we'll use example to help you, because somehow you don't want to memorize exactly just by memorization. Okay? Again, let's set the context right. So this is the program we are talking about. Okay, it's a if B, then S1, otherwise S2. We want to establish R. Okay? Basically, we're saying that if, think about what's the runtime behavior for this program. We only execute S1 if B is true. We execute S2 if B is false. And then we want to somehow to show when the program terminates, R should be the case. So the idea would be, what about we try to calculate WP for both branches separately, let's say, okay? So that's why you see something like this. Calculate WP for S1 to establish R, which means if we happen to execute the first branch, we should definitely establish R. Also, we calculate WP when S2 was executed, right? The second branch, and then you should also establish R. Okay, it's 2 WP calculated separately. We know that this WP is only relevant when the branching condition B is true. So we say B implies this. Okay? We say that this WP using S2 is only relevant when B is false. So that's why I say not B. Okay? So now here's my question for you. If you look at that, this is the first one and identical here. Okay? This is the second one and identical over here. Individually, they are. This is a Boolean expression. This is also just another Boolean expression. WP overall for this one here is only a single Boolean expression. We cannot give both. So we somehow have to combine them together. How do you combine two Boolean expressions? You got different options here. You can use conjunction, you can use disjunction, you can use implication, right? Let's not worry about implication. Okay, I can tell implication is not the way to go for now. Okay, let's discuss. Should I use conjunction here, or should I use disjunction over here? I heard conjunction over here. Guys, make sure you understand what the question is, right? Let me say very quickly again. Okay, we try to calculate the WP for the first branch to establish R. We also calculate the WP for the second branch to establish R under two different assumptions. Either the branching condition is true or the branching condition is false, right? But now the question is, how do we combine these two WP together? Should we use disjunction or conjunction? I heard disjunction here. Yeah, well, it doesn't seem we got agreement here, right? Okay, so that's what we're going to discuss, right? Intuitively, think it this way. Do we expect both branches to be able to establish R? Really? Oh, okay, no, let me put my question clearly, okay? So now, first of all, would you agree at the runtime, assuming that B is neither true or, let's assume B is not true and also B is not false. Let's say we don't go for extreme cases, okay? You might get some chances to execute S1 sometimes. You might also get chances to execute S2 sometimes, right? You don't know when. Do you want R to be established only when S1 is executed? Or only when S2 is executed, well, in both cases? In that case, conjunction makes more sense, right? The reason you might think disjunction should work is because you think about, wow, because I might go either S1 or S2, so that's why it's disjunction. No, that's a little bit that's not the way to go. But now, let's really convince you by using one example. Okay? Again, intuitively, you want to make sure in both cases, when I execute S1, R must be established. If I use S2, it should also be established. So that's why it should be conjunction. Okay? Let's consider this particular example. Okay? And we do a little bit of practice over here. Okay? This one is slightly more complicated than what we just saw. Okay, slightly more. It's an if statements, and then we got both branches as a single assignments. Okay, let's calculate them very quickly, and then we can easily see why disjunction is not the way to go. Okay, let's see this. Remember, okay, let's see over here. So now, how do I calculate the WP over here? So now that will be, first of all, y larger than 0 might either be true, or it is not the case, y larger than 0. Well, I could have said y less than or equal to 0. Doesn't matter. They're equivalent. Okay? If y is larger than 0, that means I'm going to execute this particular branch, right? So that means if y is larger than 0, that means WP for x is assigned to x plus 1. What would be the WP to establish x larger than or equal to 0? Are we okay with this? Okay. And then if this branch, this condition here evaluated to false at the runtime, just not the other case, that implies that it should be WP for x is assigned to increments, right? X minus 1, x larger than or equal to 0. And notice one thing here. You can see that's the post condition here, and post condition simply repeated twice. Okay? So far, so good. And now, can you just tell me directly what would be the WP over here? X. So that would be over here. So for this one here, X, you can think about replace this X by X plus 1, larger than or equal to 0, which is equivalent to X is larger than or equal to minus 1. Are we okay with that? Okay. Let me just wipe this out. Y larger than 0 implies X larger than or equal to minus 1. That's kind of calculation. Okay. What about the second one? We calculate WP for this particular decrement assignments to establish the same postcondition. What would that be? So, yeah, something like that, right? So you're going to replace X by X minus 1, larger than or equal to 0. So now you can replace this guy over here by X larger than or equal to 1. So far, so good? Okay, so now let's try to see why disjunction would not work. If I simply put disjunction over here, okay, we can easily give one counterexample where, well, remember what we are evaluating over here is going to be the WP, right? I can easily evaluate this whole thing here to be true, being the WP, meaning that the program is going to work always, but it's not going to work. Can anybody try to give one example? I'll give you a little bit hints. How can a disjunction be true? If one of them is true, right? Number one, hint number one. Number two, how can the implication be true trivially? Yeah, that's true, or even easier if the antecedent is already false, right? Okay, for those of you who might be already know what I'm trying to do, I can give you a counterexample. I want to see if any one of you can come up with anyone. Huh? Y equals 1, sure. So now we want to find some witness over here, right? Let's say we want to give X and Y counterexample. You're saying Y would be 1. What about X? What about I give you minus 4? What's going to happen here? I'm giving you this particular example here. Y is 1 and X is minus 4. Is the overall WP going to be true or false? Are you sure it's be false? Are you sure? I can say it's trivially true in the following way. Let's keep this counterexample in mind. It's going to be minus 4 and 1. Okay? So now, how do we evaluate this? Okay, so that means this one here is just going to be false, right? Because 1 larger than 0 will be true. True negated would be false. So that means the whole this implication over here is just going to be true. And then true or anything will just be true, right? So the whole thing is going to be true. However, is true the right answer, is the logical answer over here? It should be false. Why? Because you can see over here, given that X is minus 4, minus 4 over here plus 1 will give you minus 3. You're not satisfying the postcondition. This one goes a little bit deeper. What's the conclusion here? If you actually use disjunction, you know, every logical reasoning we are doing here is sound. We're not making any mistake. However, the conclusion simply gives us something that's weird. Why? Because the WP rule that we try to experiment, which uses disjunction over here, is simply not the way to go. It should be conjunction, which means both branches should be considered. Okay. Question here first.
Y greater than 0 is, for this case, it's all is true, right?
Which one?
Y greater than 0 for the first one, because we are using -4 and 1, right?
No. Here, no. first of all, do we agree that we're going to use this example here, right? Yes. So x is -4 and y is 1. Yes. Okay? Y is 1, so that means this particular part is going to be false. Agree? First of all, if this antecedent is false, that means the whole implication over here is going to be true. And once this is true, since we're using disjunction, it doesn't matter what this is. Doesn't matter. However, in this case, it should be true. Because now, if you use the -4 over here, -4 plus 1 is going to give you -3. -3 is going to violate this postcondition. So that means this particular WP rule is not valid using disjunction. Okay? Let's now do one more thing to help you, okay? What if I try the following? What if I try the conjunction case? Okay? If I try the conjunction case, let me do it again, okay? I want to do it properly. Let me start a new page over here. I'm going to use the same example. Finally, the correct rule to use is like this. It's going to be when y is actually true, y larger than 0 is true, implies the WP for the first branch, x is assigned to x plus 1 to establish x larger than or equal to 0. Okay, the second one, when it is not the case, y larger than 0 implies WP for decrements, x is assigned to x minus 1, and then the same postcondition. And this time I'm going to use conjunction. That's the correct way. Okay? Let's use the same example that caused us trouble before. Let's see if this time it's going to cause us trouble. Okay? And now I'm going to use -4 and 1. Okay? And then we're going to try xy being -4 and 1. Okay? Let's say we try that. Now this time what's going to happen? Let's follow the same order of evaluation as before. Okay? Y is simply just 1. What's going to be the evaluation for this? False, right? The whole thing will still be true. And now, when one of the operands for conjunction is true, can we conclude whether it's true or false right away? No, because remember, it's so-called identity of conjunction. P and true will just be P. That's why. On the other hand, P or true will just be true. Okay, it's a straightforward application of what you learned before, but anyway, in a more programming context. So now, so that means since now y is simply larger than 1, so the other case is simply not applicable. We just discard it. Okay, it's not going to affect the result. But now y larger than 0 over here is true. And then for this guy here, let me copy over. Okay, I forgot to copy over. This one here will just be x larger than or equal to -1. Larger than or equal to -1. Is that the case? X, the one we chose is -4. -4 larger than or equal to -1 is false. So overall, it will still be false. That simply tells us, for this particular case, you just cannot establish that postcondition if you choose this particular counterexample. The reason I'm doing this exercise to show you is really to show you why you should really choose conjunction over here as opposed to disjunction to reflect the fact that both branches must be able to establish the postcondition, okay, not either one. If you choose disjunction to say either one, you're going to run into a problematic scenario. Okay? Question? Yes, of course. Which one? I mean, this one here? Yes.
So here you calculated -4 is larger or equal to -1. Shouldn't you just increment 1 first?
Hmm?
You only have to increment 1.
Oh, no. The reason, okay. First of all, let me undo a little bit. Oh, actually, remember what we calculated before? So we're going to calculate the WP for this branch over here to establish x larger than or equal to 0. And that should be x larger than or equal to -1. Remember? From the previous one. Okay, good. So now over here, what I started with is x larger than or equal to -1. That should be the case. But now, this particular counterexample that we choose, x is simply just -4. So that means it's invalid input value over here. Hmm? Oh no, you can think about 1 and -4 here are the pre-state value that we are going to try. and it's not going to satisfy this particular. Well, think about this. If you, let's say in the beginning of your program, in the beginning, if I simply give to you x being -4 and also y being 1, that's how we start with. Is this going to establish the post condition over here given this particular program? No, because over here y is equal to 1, so that means we're going to go into this particular branch over here, right? But now x is -4, so -4 plus 1 will give me -3. I will violate that, right? Yeah. Okay. So you kind of confirm. No worries. That's fine.
With compounds or nested if statements. So, for example, in this case, we have B implies and B implies, or not B implies.
Yes.
For nested, we have B implies, or
Yeah.
not B.
The question is, what if you got nested if? Yes, you're going to get nested implies. Yeah, but we don't have to go there just yet. We'll see some example a little bit later. Okay, just make sure you're comfortable with the basic case first. Okay. Okay, any question about this? Okay, is this important? Yes. That's why I spend time. Yes, Uma. Uh-huh.
The post condition would be something like B implies something and then not B implies another thing.
Oh, like what the post condition we wrote before. Yes, you may. In that case, let me, you know what I can do? In the last class, let me choose one of the common post conditions you had to write before and show you a little bit of the rule. I didn't want to mention them today because we just started up, so it could be a little bit complicated. Yes, yes, I'll try to see what I can do in the next class. Yes. Okay. Okay, if no question here, let's go a little bit further. Okay, just to at least we can finish everything until we have to introduce a loop. Okay, hopefully. Okay, again, it should be conjunction. Okay, that's a conclusion from here. But you got to know why. Okay, I'll go over this proof rule maybe next time. Okay. Okay, so now let's say this. Is this program correct? Let's say this. The precondition is x larger than 0, y larger than 0. The post condition is bigger, larger than, or equal to, smaller. Assuming that bigger and smaller are some global variables, let's assume. Okay? And the program here is simply just an if statements. To be honest, I'm being a little bit unfair because we are using sequential composition. We haven't introduced them yet. But given what you have seen, how can we do, to what extent can we derive the logical expressions?
Question instead of, are we going to change the post condition or just the precondition?
No, that's what you're given.
Okay.
You're given this particular precondition here, x larger than 0 and y larger than 0. You're also given that fixed program. Okay? You're also given that post condition. My question is this correct? Well, this one is, okay, yeah, question.
Yes, if you give us a bit more into first to do with the.
Yeah, actually, what I would like to do is do this a little bit. Okay, for this one here, let's say you're given this problem over here, right? Again, how should you solve it? The two steps I talk about, right? Step number 1, calculate the WP. Step number 2, you want to see if the existing precondition here implies that WP, right? So those are 2 steps. For step number 1, I want to do a little bit just to start you with because we haven't really talked about the sequential composition. We will. That'll be the next topic. But before that, let me see what we can do. Okay, at least we can do a little bit. Okay, step number 1. Okay, calculates. And also in the exam, let's say you're given this, it would be okay if you try to say, I'm gonna name this guy here to be S1, if necessary. I'm gonna name this guy here to be S2. You can save some writing over here if you wish. Okay, like what I'm doing here. So now let's say for S1 and S2 individually, we haven't learned about sequential composition, but I will do that. But before that, we can already do something. Okay? Calculate the WP for if x larger than y, and then I will do S1. Otherwise, I will do S2. And then the post condition will be bigger, larger than or equal to smaller. Okay, I'm just sketching it. We can calculate that. That's the first step, okay, whatever it is. I'll continue a little bit, but let me tell you what the second step is. The second step, you want to say the existing precondition over here, prove or disapprove. Prove or disprove. The following. X larger than 0 and y larger than 0 implies the WP, which is calculated. Okay, I'll just say WP here so you understand. Okay. Let's go on a little bit more for number 1. Okay, a little bit more. For number 1, how can we continue for the next step? Well, actually, what's the overall structure over here for the program? Is it assignments or is if conditional, right? Okay. So this is what we can do. Okay. I would say it's equal to, okay, according to the WP rule for conditionals. Okay, that will give to me 2 WP, right? Combined with conjunction. X larger than y, or conjoined with the case. Let me just make myself a little more space. Okay, like that. Okay, and also not the case, x larger than y. Okay, notice that it's conjunction, okay? Like what we discussed in the last 10 or 15 minutes. If x larger than y, so that should imply the WP for S1, right? That's a branch. For S1 to establish bigger, larger than, or equal to smaller. I'm just repeating this post condition for the first time. Okay, and then if it is not satisfied, I'm going to execute S2. So it's going to be the WP for S2 to establish B larger than, bigger, larger than, or equal to smaller. That's as far as what we can do up to now, since we haven't learned about sequential composition yet. So we cannot break S1, S2 further, but we will. Okay? So this is what we can do up to now. Once we talk about sequential composition, I will not revisit this example. I will leave it to you to complete it. Okay? The next topic will be about what if you got semicolon to combine things together, like one statement follow the other. Okay? Let's talk about it. Oh, that's exactly what you'll see on the slides, but I thought I might just show you the detailed step. Okay, this guy here. This one is the most interesting one. Well, loop is also interesting, but this one is more interesting than assignments, if statements. Let me give you a little bit intuition over here. Okay. The intuition is when you try to execute S1 followed by S2. Think about this is the pre-states. And this is the post-states. And as far as the post-states is concerned, we wanted to satisfy R. Agree? The post condition. Okay, let me write it on there as well. Where R should be satisfied. But now the problem is S1 and S2, they do not start in the same states. Agree? S1 does start with pre-states. What about S2? It starts in the intermediate states after you have executed S1. You see what I mean? So this is an intermediate states. For S1 to start with. Oh, yeah, S1, S2, yes. That's one thing to think about S2. I would say that's point number one. Are we okay with the point number one here, right? That's an intermediate state for you to start S2. Then point number two is even more important. That will help us to come up with the WP rule. This is also the post states that S1 may establish. Let me put it this way. You want to combine 1 and 2 together in the following sense. In order for S2 to establish R, it's better that S1 establishes something that's good enough for S2 to start with. You see what I mean? Okay, let me say that again. Eventual goal is to say upon the termination of S2, we want to establish R. However, it relies on the following assumption. Because S2 only starts in this particular state, that's after the execution of S1. So it better be that when S1 terminates, or when S1 terminates, it will be enough for S2 to establish R. So we talk about two ideas about the WP. Okay? Let me switch to a new slide and talk about it. Again, we got S1 over here. We got S2 over here. So this particular intermediate states should be good enough for S2 to establish R. Okay, again, this is upon termination, this is going to establish R. Okay, so now let's think about the formula. What would be the WP for S1 executed after S2 eventually to establish R? Any idea? I'll start you with a little bit. WP for S1 to establish something. How do I specify the intermediate step? What's that intermediate state? Exactly, exactly. Remember what we said before over here. This intermediate state is such that it will be good enough for S2 to establish R. When I say good enough, I'm talking about WP, really. Yes? Exactly, that's exactly right. So what you observe is exactly correct, as we said over here. So you can think about this particular intermediate states. It's exactly the post states already here. It's the post states of S1. At the same time, it's the pre-states of S2. That's exactly right. We want to make sure the post states for S1 is good enough for S2 to start with, so that it's going to establish R. Okay? So now over here, what we will do is WP for S2 to establish R. So that's the rule. When you first see that, it's a little bit weird because one WP now suddenly becomes WP. Am I going to get exponential growth on the WP eventually, so I'll never end? That's not the case. Eventually, you will hit some base case, like assignments, eventually, but not yet. Nice. Any questions? Up to now, I just try to explain to you what a rule really means. Okay? And of course, this is based on the insight into sequential composition. You got some intermediate states. And that particular intermediate states is the pre-states for S2. At the same time, the post-states for S1. So that's why S1 over here, if you think about this part here, I'm talking about once we execute S1, it must be good enough for S2 to establish R. That's why you got 2 WP over here. Okay. Questions before we do some example? Yes. Yeah, so what will be the order of evaluation? We'll see, don't worry. Yeah. But for now, just understand this particular principle here. Yeah?
Just for any number of NFS then.
Aha, so good. So now, apparently, in each arbitrary program, you may not just have a single semicolon, would you? You'll be very nice, but it's not the case. Okay? For example, let me just do one more for you, okay? Just do one more. Let me just make it a little bit more complicated, slightly. Let's say we got, what will be the WP for S1, followed by S2, followed by S3. Establish R at the end. How many WP should I write? 3. Okay, let's try. Think about this. I'll just mention verbally quickly. Okay. Upon termination of S1, it must be good enough for S2 to start. Upon termination of S2, it should be good enough for S3 to start, eventually to establish R, informally. Okay? How do we write it? It will be exactly equal to the following. The WP for S1 to establish something over here. That thing over there should be good enough for S2. Good enough for S2 to establish something. Yeah, so that'll be a WP, right? Okay, I just want to make sure. And that would be for the WP for S3 to establish R. So 3 WP. And depending on how many lines you have, going to have this many WP. But I'm going to do an example, don't worry. I want to just explain to you conceptually that's how you think. Yes?
So the WP, like the very outer one, is that going to be the weakest one?
The question was, is the outermost, the blue one, the WP is going to be the weakest one? Not really. You can think about that's the WP eventually we want to calculate.
So is the orange,
You can think, how about the order of evaluation? You realize, okay, we're thinking this way. We wanted to calculate this guy here, right? In order to do that, we want to do the WP for S1 to establish something. You can think about this thing here. Before this thing is known to us, we cannot calculate this WP. So this WP for the moment is suspended. Like I put onto the stack. How about that?
That's why I assume it would be the weakest one,
Yeah.
because all of the other ones.
No, you don't want to say weaker or stronger, because usually when you say weaker or stronger, you talk about proving implication. That's not relevant over here. Yeah, it's more about order of evaluation. In order to calculate the final outcome, turns out you have to calculate this one first. After that, you can calculate this one over here. After that, you can calculate this one here. That's going to be order of evaluation. But we'll see example. Okay? Yes?
What is the level of length we can expect on a file?
What would be how many lines of code you have to?
The length of
I wouldn't want to commit at the moment. I can tell you last year, the student had to verify a program up to 10 lines. Well, I'm not saying 10 sequential composition. The program itself has a loop. The loop itself, the body of the loop has only about 3 or 4 lines for the body. So about 3 or 4. I think that's about reasonable. But I will give you some practice exercise at the end of the course, so don't worry. And you got time to do it. All right, let's now do one more exercise together. Okay, and then, okay, let's do this one here, okay? Is this program correct? Oh, by the way, what's this program doing? Swap. Good. Now, we prove what you did in, maybe you guys already did a swap program in 1012, right? But now you can prove it, right? So now, is this program correct? We'll see. Okay, again, we got 2 steps, agree? Okay, step number 1. okay, calculates, you know what, let me be careful with the color I'm using, otherwise you'll get confused very soon. Calculates the WP for the temp is assigned to X, followed by X is assigned to Y, followed by Y is assigned to temp. And what we want to establish at the end is X larger than Y. Right? Calculate that first. And step number 2, you want to make sure true implies that. Okay? That's an overall picture. Okay? We got 5 minutes, right? So you want to make sure. 5 minutes. I'll do a little bit, and then I will definitely complete the rest, but you can also do exercise. I want to impose one interesting exercise for you as well. Okay? I'll only spend out 2 minutes or 3 minutes. Okay? Let's try to see how it can be done. What I can do is think about this guy here, blue, and this guy here, pink, and third one, orange. Okay, what it is going to do is like this. Okay, let me just do the first one. Equals, okay, you're going to see WP rule of, you can say sequential composition. That's fine. I'm okay with that. Okay? So now it's going to be the WP for temp is assigned to X. For that, to establish the WP for X is assigned to Y, followed by Y is assigned to temp. Oh, of course, this should be a semicolon. Okay? Be careful. Okay? And then after that, I'm going to have over here X larger than Y. Okay? And let me close them properly. Pink. Okay. That's the first step. Any question about this? Oh, not yet. Not yet. I'm trying to do actually all the steps actually. But you can see the program over here. Oh, good question. I'm glad you're paying attention. This guy here, I haven't really split it yet. I will. Okay, don't worry. Okay. Okay. Let's do one more step. Okay. And now I'm going to say another WP rule. Of sequential composition. I'll make sure I got 1 minute. I want to give you a challenging interview exercise, a real one. Okay, one moment. WP over here, and then we got temp is assigned to X, followed by, and WP over here, X is assigned to Y. So now we can apply the sequential composition, right? So now it's going to establish the WP for Y is assigned to temp. And at the end of that, we should really establish X larger than Y. Okay? It should be orange, pink, orange, pink, and dark. So now, the order of evaluation goes like this. I'll mention to you, I will complete that next time, but do try that yourself, okay? It's going to be good preparation. And then I'll pose one question to you, and then we are done. The way to unfold this guy here is you can definitely calculate this guy, agree? By substituting, you can definitely do this by substituting every free occurrence of Y by temp, okay? Once you have done that, you can now complete this guy here. Once you have done that, you can complete this guy here, okay? Do one by one. See what you get. Okay, I'll continue from here. Now I want to give you an exercise. One of my students said to me, it's an interview he got for his job. Here's the thing. Let's say I want to swap X and Y without using an intermediate variable. That's the question. Is it possible? think about it. Oh no, it's no depends, right? Basically, you're gonna use. Don't use if then else. Don't use any loops. Don't use any method call. Just use x and y, and some simple arithmetic, without any intermediate variable. And you want to swap x and y. They're numbers, yes. Forgot to mention. Yes, they're x and y. They are numbers. Yes. How do you actually? What doesn't matter if they're even if they're objects. Oh, sorry, they are numbers. Yes. Yeah. Yeah. No worries. Yeah, I think it's a legitimate question. Yes, they are numbers. Okay, let's say x and y are numbers. Okay, here's my challenge to you. Okay, number one, come up with an algorithm without using any intermediate variable. Number two, prove it. Okay, think about it, and then I'll stop here. I'll see you next Tuesday. Tuesday, I'll talk about the exam. Make sure you come.